parametric model. And so the idea is we're going to assume, right, we're going to assume that this regression function has a parametric form, and that parametric form represents sigma t transpose x. And so this simplifies the problem a lot because among all the possible regression functions, we are just looking at regression functions that look like this. And so if the model is like this, then the optimal rule, right? The Bayes rule is the one for this classification rule for the 0-1 loss. So threshold is at 1/2, and so 1/2 here is 0. So you would get a decision boundary which is theta transpose x equal to 0, right? And let's see, we have it here. Yeah, so you would get a decision boundary like this. And then as I vary, for example, so if you think of the decision boundary would be where all the x's are sigma to the phi transpose equal to 1. And then on all the other level sets, this function. So level sets is where this is equal to all the x's for which this is equal to a particular value. For example, all the x's for which this is equal to 0.9, those have the same probability of y being equal to 1. And so all those level sets are in these lines or in general hyperplanes in R2. And then you can see the direction, right? So you have the direction which is specified by our star, and these lines or hyperplanes are orthogonal to that. And as you move along theta star, theta star transpose x gets larger. So these are also like increase in that direction. And so you can see to this side above that decision boundary where theta star is pointing is where the regression function is bigger than 1/2, so you have the class 1 solvent by the Bayes rule, and below it, the regression function is less than 1/2, so you have 0 assigned by the optimal rule, right? So, and then I talked a little bit about that. The actual labels of the points, so let's say you generate from a model like this. So if you want to generate from the model, it's not enough to specify just this parametric form, because you also need a marginal distribution for x. So that will depend on what you want to do. But say a model is like that, normal zero covariance identity. So this is a hopefully you know the points are sort of scattered in the R2 plane everywhere, but closer to the center or the origin, and then equally spaced around the origin. So circularly. And so that's the marginal. This is the conditional, and then the point is a lot of the points that are near the boundary do not have. So, for example, the points are above the boundary. They're not necessarily, for example, here. The two labels are the labels that you observe when you generate from this model is not necessarily 1, although the optimal will assign 1. And anything below here is not necessarily 0. Okay. As you move away from the boundary, because this probability gets very close to either 1 or 0, you get even more certain. So there's the points that are way below the decision boundary that are pretty much almost surely assigned 0, and the ones that are above there almost surely assigned 1. But near the boundary, things that are difficult. Again, there's some noise in the problem, which is just the difference between the label that's assigned by the Bayes rule and the true label. So if you think about this, you sort of understand. So the difficulty of the problem, there is this fundamental limit, which is the base error, that if you can let it go, no matter what kind of classification and sophisticated classifying the design. And that's because of this inheritance. This is the best we can do. And the best we can do just like this, and then we take the price of this class about the background. And so we also talked about the way that we can control them. And if you think about normalizing this theta star by its norm, so you can divide and multiply by theta norms at the start, and then you see that which direction is gonna define the hyperplane. So the hyperplane that defines the decision boundary. If you look at it, it's theta star times like this. It doesn't change by using theta star. So if I divide theta star by its norm, for example, by a number, this hyperplane doesn't change. So the decision boundary is from variant to scaling of theta star. So this is all defined the same decision boundary. What the norm of theta star does is like control the signal polarization. Okay, this is very large. So now you look at it a different way. So you can define a new sigmoid function, which is like that, and then I can apply this to this normalized vector. So when you start transpose X. So this redefined sigmoid function, you can see if you plot it when theta star norm theta star is large, and it has a very sharp transition. The norm theta star is very small, it has a very gradual transition. And the transition here is sort of to tell you how fast you switch from class 0 to 1 as you cross that decision boundary. And so you get more noisy data if the theta star is small and very sharp boundary of theta star, more theta star is large. Okay. Any questions? This is like a recap. Yeah.
You said that there is some inherent noise in it, right?
Yes.
Oh, can you tell why is that again?
So can anyone tell me, based on what we discussed, why there's an inherent noise in this model? So the noise is roughly the difference between the true label and the label assigned by the base classifier.
That is because it's a hyperplane and not a curve.
No. It doesn't matter if it's a curve or a hyperplane. It's because this probability is not going to be 0, 1. It's like between 0 and 1. So the points, there are points here that get assigned probability 0.5. There are points that get assigned probability 0.6. There are points that get assigned probability 0.99, for example. The points that are so this model allows you, so this sigma is gradually changing. It's not like a step function. So this means that for some x's, this is not exactly 0 or exactly 1. Okay. And so when you generate from this model, if I fix that x, sometimes I get 0, sometimes I get 1. Okay. So suppose you can do it in code. I'm going to show you some code. But let's say I fix x, right? Fix x. And then theta star transpose x is 0. So sigma 0 is 1 right? So if I now have that x, let's say condition on that x, when I generate the label, there's 50% chance of coming up 1 and 50% chance of coming up 0. And I can't know ahead of the time. But every time I generate, I get a random choice. And this is not avoidable, right? So you can't tell. So all I can see is x. I can't detect y perfectly based on it. So that's the inherent noise as well. So if you think of image classification, for example, this is something worth thinking about. So sometimes, so machine learning, one of the top applications is vision. So you have the classical problem in vision is classification of images. So you show me an image,
I'll tell you if it's a cat or a dog or a horse. This is the simplest case. And in some cases, if you show me an image, I mean, you can imagine that this image is going to be a horse for sure. It's not going to be like a cat or a dog. But there are some images that it could be a cat, it could be a dog, okay? And some situation it might be a cat. It's harder to argue it like that. But in the vision, it's like finding. So it's like it seems like, for example, in the vision problem, there is a very sharp boundary. It's like the cases in which like there's uncertainty in the label of the true label of the image is low. But you can imagine there's some cases, like for example, blood pressure, cancer, etc. There could be like all the features, like all the characteristics of two persons are the same. One gets like this outcome, the other gets that outcome. And it's not possible to tell. Sometimes you might imagine that there is some latent variable perhaps that you are not including. But that latent variable would drive into the trend. Maybe if you knew all the hidden variables, then this would go away. And for the physicists have worried about this. So the reason about quantum mechanics and stuff like that are the local like hidden variables that you don't see that causes these random phenomena, causes us to see that this land, for example, whether the random label that's on this boundary. So the point is on this boundary, I get a random label because there's another variable that I don't see. But if I see that, then whether we know it or not, I don't. So that's a different question, right? But once you have this X and you model it like that, then there's inherent noise, whatever the source is. So you're not like modeling, so you're modeling this is probability distribution. So in any case, so too much off topic, right? But is it not clear? So
Yes. And you said that we can increase noise by increasing the magnitude of the data.
yes. Yeah, so that's another point which is often I would say overlooked. The people, for example, look at logistical that they want to like model, simulate data for classification. They generate from this, for example, and then they want to increase the noise, they just add, like flip some of the labels that random. That we can do, but there's like an actual way of doing it, which is controlled by the data. One last point then is if I let what happens if I let this go to infinity, the normal data start goes to infinity. Because also, yeah, it becomes step function, that means that like I can like perfectly separate, right? And so if you reason backward, in the cases where you have actual data, suppose you have actual data, and you try to fit this model, and there is perfect separation. So you can linearly separate everything. So these are called linearly separable cases. So I have one class, which is here, another class, which is there, in real data. And there is a perfectly, and then there's a perfect classification. So I can pass a line here, for example, that separates the two. Then you can imagine that when you try to you weirdly pick this, the theta star might go to infinity. So that's what would happen. If the existence of the maximum likelihood. So we went through the maximum likelihood, and that leads to this loss minimization that we want to do. But if you're dealing with a case like that, you might see that when you start to optimize, your parameter starts to go into. That's fine. So as long as the direction is right, so you care about the direction, you really don't care too much about that. So after a while, the direction is stabilized. It's still going to infinity, but along a direction. So you that direction gives you the precision boundary. All would be good. Yeah. Questions? So I want to go through the code a little bit, try to implement. So the other thing that we did, which was a while ago, is how to fit this model, and we started with this general framework. If I give you a parametric model, I can look at the maximum likelihood estimator, which would be maximizing the likelihood, and the likelihood of this model is the probability that observed y1 of y and given x1 of x n as a function of theta. So this is independent of theta, and because of the IOD assumption is factorizing into these marginal conditional distribution or densities, or in this probability mass functions. And so this we model as the Bernoulli, right? So it's Bernoulli, it's sigma theta transpose x5. That's another way of saying the probability that y1 I equal 1 then x5 is that. So this is equivalent to the Bernoulli characterization, or like the statement. So these two statements are the same for a random variable that takes just value 0, 1. So we have this factorization by independence, and then we have this shorthand notation, which I hope you remember, and then you take the log or the negative log, and then you try to minimize. When you take the log, negative log, try to minimize, the problem reduces to this is the general form. This is the MLE, maximum likelihood estimator, in the empirical risk minimization form. So this is really essentially you're minimizing a particular empirical risk. And in the particular case of the model that we have, the negative log likelihood like that, and you can write it down. And this particular form we call this BCE, binary press entropy, because machine learning people call it binary press entropy. And it's related to press entropy between two Bernoulli variables. So that's defined like this. So the loss is between the label and the probability. Okay. So 0, 1 here, and then something 0 and 1 here is something to 0, 1. And given that, I can write it in the simple fashion where g theta of xi is this sigma theta transpose xi. And I'm minimizing over theta. You can see this falls within the framework of integral risk minimization. I have a loss, measuring so the distance of a loss between the true label and the predicted label. But this is not the label, it's just the probability, but the loss is defined between the true label and the prediction, like the probability of, or predicted probability of the label, which is fine. This is a parametric family, so it's like a function. So as theta varies, these functions define the function class g theta. And so we're really doing empirical risk minimization for a restricted function. And if I absorb this g theta, so sorry, this g theta has a sigma in it. So this is g theta. So if I absorb the sigma into the loss, you do some calculations, and there's this simpler form. So I can write everything like that, where now instead of that g theta, the linear function appears there. And this loss is now this loss, which we call this log loss. Okay. So the two problems are equivalent, and you can see there is a bit of the part of the function that we were trying to use as the predictor is now inside the loss. So if you imagine this happens, so I absorbed it into the loss function. So my prediction, for example, if you want to do like I'm going to like introduce some like notation or like diagrams that are useful in neural networks. So you have your input, which is x, right? It passes through a linear function. I'm going to do it like that. Okay, so this goes to like, so let's say it takes an input, just produces an output. So this is like, it's a little hard to do. So let's see if I want to. yeah, maybe I'm not, okay, so let's not do it. So just linear map, okay, linear. This goes in and something comes out, and then there is this non-linear map, which is sigma. Okay, so that's our model. So this takes it, produces theta transpose X. And so that's the linear map. X goes in, and then this produces sigma theta transpose X. So that could be our model. And then our losses that you see, or I can cut the model at this point, right? And then absorb this into the loss, which is often easier. Like, so that's what we're gonna do most of the time. Because this is constant, like this, there's nothing to optimize here. I can just push it to the loss. So we'll go to the loss. And then so the output here would be the meaning of the output is the probability. The meaning at this point is, anyone remembers? The output here is. These are the log odds or logits. Okay, so our model can predict the logits or can predict the probabilities depending on what level I stop, but the end result is the same. So most often we work with this kind of version. It's easier. Okay. All is good. Good. So this is the logistic regression setting, right? And what I'm going to do is I'm going to generate data from the model that I mentioned. And it's worth remembering that I can write here. So I can write X theta star, and this is X1 transpose of X1 transpose times theta star. And so this gives me X1 transpose theta star to the X1 transpose theta star. And so the I flow of this, right? So this matrix or this construct appears in linear addition as well. So this is Xi and this is theta star. So I can put the data points the training X's in a matrix, which we call a design matrix. No, but in any case, the X's are in the matrix, and if I multiply by theta star, I can basically produce the output of this linear map or linear layer, if you want, at every data point. Okay, so really, we'll see like a linear block is just something that takes, let's say, X and outputs theta transpose X. And this can be modeled as like X times theta star if I have a bunch of input. So usually, remember, we want to calculate the output of these blocks for multiple inputs, because of multiple training or multiple tests. And so I give them as a matrix, which is n by p, and the output would be, in this case, n by 1. Okay, so that's the output of this linear map or linear layer. And okay, so that's good to remember. Now the way I'm generating 500 samples. This uses NumPy. Normal rand n is normal, so we create a normal random variable 500 by 2. Okay, so these are the rows are training examples, and everything is two-dimensional. I'm going to set SNR equal to 1. This is not necessarily SNR, but it's just a measure of SNR. So that's the factor that I multiply theta true by. So theta true is like a vector, 3 and 3. So it's 45 degrees. But representing the 45-degree line, so the decision boundary is going to be orthogonal to the 45-degree line, the plane. And then I define the probability. That's the probability of observing one. So this is really the, if you look at this closely, this is the sigma, basically. This calculates the sigma theta, let's say true, theta star transpose xi for all I, because these operations are coordinate line, so this x pi at theta to remember at is a matrix multiplication, so I give the root of matrix multiplication. It produces that n-dimensional vector, the output of these linear maps, and then I apply the sigma. The sigma is 1 times 1 plus e to the negative. So this is really 1 over 1 e to the negative. Theta star transpose xi, and I'm generating this for all I from 1 to n, putting them in a matrix. Sorry, because in this case it would be a vector n by 1. And then I'm going to create a binomial random variable with one observation, which we keep varying essentially, and these probably that's probably so it produces an observation. So this is flipping the coin with the probably thing. So that's how we generate the model, and then I'm going to plot it. See if it plots. So that's the data. Okay, so you can see there Gaussian. So if you ignore the labels, this is a two-dimensional Gaussian with identity covariance matrix. And one thing that we can see here is the noise. So we can also see the decision bound a little bit. So the theta is in this direction. So decision bound is power into that direction. So what would happen, for example, if I change this SNR? So let's say if I change it to 0.1, what do you think would happen? So let's see which way it goes. It should be worse. So you can see it's worse. Okay, this is still logistic regression, but now because that transition function is very smooth, so everything is mixed up. So all the points are like, so you have to weigh here to be 0, you have to weigh here to be 1. The decision boundary is still there, but like the area around which that things are uncertain is wider. So if I turn it into 10, so you can see there's a sharper. Right. And I think we can't see much more sharper than this, but it's very sharp. Yeah. So you can see like so that's the effect of the size of data. Okay, so this gives us like a reasonable amount of noise. And sounds good. So that's the setting. Okay, so this just transforms these NumPy arrays to PyTorch tensors. This might not be the best way from NumPy, and it just transfers. This keeps the data, apparently keeps the data in the NumPy array, it doesn't copy it. So these are like technical details we don't have to worry about. Another way of creating is just to do Torch.tensor and pass the NumPy. And this float is, it's going to be like a lot of frustration is going to be caused by this because there are different data types. There's float 32, there's float 64. And sometimes when you create and don't specify the types, some Torch tensors like in float 32 might have float 32 types, some might have float 64, and then you get an error when you try to multiply or operate. So the here float is float 32, so it's good to make sure everything is that's the shape. This is D type, data type. So it's float 32, and hopefully we're going to be okay. So there's a default type that by which these are created, and I want everything in that. So this is the labels, and this is the data, right? So these are now Torch tensors, and I can, for example, look at the first phi. And the labels as well. Okay, now we want to do the logistic regression, and we're going to do this version with the log loss. So that's the log loss, and this is my empirical risk. And I just have to implement this loss, or we should call it risk probably. This is what is doing that. So I give this function theta to calculate x times theta. Matrix x times theta that's these values, and so minus y times z now is this. And so this operation is, so this is a vector, y is a vector, z is also a vector. So this would be 0.5. I will calculate y by transpose theta star from all i's and put them in the vector. So this is ln y multiplication of two vectors. And this is just what this is. Torch log 1 times vortex, just this log, this part of the loss. So we're eating and then we take a mean. So that produces this average. Okay, so that's our loss. So here I've like started, this is the start. T minus t. And then I've written a function gradient descending momentum. I pass in my loss, theta, the value of the momentum which we talked about, learning rate, and then with the sets. So this is actually much better. So we haven't talked about this, so let's do this. This is the basic gradient descent. So basic gradient descent is similar, there's no momentum to go. Loss, theta, learning rate. So we're going to go into that and remind you what this is, but this is basically essentially like the function that abstracts away what we did last time. So we wrote the gradient descent, and then the entire procedure is the same. The only thing that changes is the loss. So now I've written a function and pass the loss, and it just does the gradient descent algorithm. Some people call gradient descent like a meta algorithm. So whatever your problem is, you set it up and the gradient descent sort of solves it. It's an optimization algorithm, but it's meta learning. So it learns on top of, let's say, classification or regression or language model. Okay, so I'll just dig into that, but you can see the trajectory. So the snot plus trajectory, we started from 3 and minus 3. So that's the starting point. And then we like descend along the level sets. If remember, we talked about the gradients are always perpendicular. If the step size is small, perpendicular to the level set. Okay, so gradually moves here, and you can see it's like fairly slow. Fairly slow. That's where this momentum idea comes in. You can see if I do this, which we'll talk about later, that does a much faster move. So the same learning rate is one. So let's do learning move. Let me use the same learning rate. This is the step size, which people in machine learning call learning rate. So this is like step size 1 with gradient descent. You can see it gets here, and here gradient becomes very small. So every step takes a long time. You have to do very, very, very like many steps to move. This momentum, the idea is that, okay, I've been moving, I'm gonna push myself no matter what the gradient is. So it's gonna use the previous gradient basically. So you can see it moves much faster. So the same learning rate, so it pushes around and that's some crazy sort of switch and comes back. And let's see what the end result is. So we're pretty good. So let's see, like this is the last. So take a list here is going to give me. So this gives me the output of this is going to be a list of the loss functions along the way and a list of tables that they are taking. And so this so the -1 just takes the last element of that list. So if you look at theta list, Oh, I think it gives me, okay, it's a list of tensors, right? So each one is, so you can see it's like bracket is this. So start from 3 minus 3, and then this moves on. And then let me show you maybe the last 5, the last 5. The last 5. This is not the last. The other way?
Yeah, the first one.
Right. Last 3. Good job. So this is like -5 to n. 1, 2, 3. So you see, like the moves are really slow, right? But you're settling around the correct value, okay? But this is the difficulty with regression. It's like with logistic regression. So let's see if I can plot the loss as well. Plot the loss. Okay. So that's how the loss goes down. If we do the gradient descent, how does the loss go? Okay, not bad, but we'll see. So you can see it's like we're still like further away from the entry, right? So it gets very slow. When you look here, the gradient is very small. And so you can also see the loss has this flat region. So this area is pretty flat as opposed to linear regression where things are bowel shaped. So when you come down to like a small region, so regression doesn't have this problem. So like with quadratic loss, if you start coming to the area where things are close to being the gradient close to 0, usually like you have enough curvature. So you're not gonna have this could also be hard if it's like that. But in this classifications, things like might be like this. Okay, so in a certain direction it goes to 0, but then it got like I think it's like very slowly went back up. So you have a very large flat region, and then moving through this flat region is hard. And that's where the momentum idea comes in. So I'm going to go through the details of these two shortly. Any questions about that? That's a very easy way of solving the logistic regression. So that's a great R gradient descent. So what it does is it takes a loss, which is going to be a function. Here in column beta to be theta, that's the initial parameter. A learning rate, which is basically the step size and the number of steps. I'm creating a NumPy array or NumPy vector to hold the loss. I could have used the list, and then also a list to hold the betas or thetas. Okay. So this initializes with the original beta, and this clone is important. So if you drop it, anyone knows what would happen. So this kind of initialize it with beta, and that beta changes later. This is going to change. So this is going to be a reference to the initial beta. So when you clone it, to copy the version of beta, and later when you change beta, this is going to remain as the initial value. So if you don't, so this is fun to debug if you haven't done this, and it's going to take a very long time to figure out why everything is the same. So remember, if you want to copy, because things are more efficient if you pass things by reference. Default is like things are reference to things that are in memory. So for each step size, we do calculate the current loss. So apply this function to beta, report the loss. So the current loss would be a tensor of size 1. This is item extracted that's out like the value. And then you do this current loss dot backward. What does this do? This is the, like the magic. Anyone remembers what this step is? So when I calculate this current loss, this is a function of beta. And beta by default has, we are hoping that has that required grads properly set to true. Okay, because it's true. When PyTorch calculates this function, it also keeps track of the nature of the function. And when I apply, so this is going to be really a function of beta. It's not just a value, but the whole like mechanics of how it's generated is stored as a gradient function. So it calculates the gradient function. And so when I do this, it evaluates the gradient of this loss with respect to every vector. In this case, there's only data, but we could have implicit other vectors in when I created the loss. If there are other, so this is how it's created. It's interesting, it's created inside a different function. But because these things are passed by sort of reference, this is a little bit tricky to understand, but when I pass the theta here to this theta is pointing to this tensor. And this theta, we just renamed beta, it's called beta in that function, but it's still the same thing. And then when I call the loss, it's going to call the loss, it's going to be the same sort of object all along, and this operation is applied. And so PyTorch knows that when I do the loss backward, it has to come and update the gradient of this guy. Sorry, the gradient property of this guy. So it takes the gradient of loss with respect to the vector that went into building. So if you have a vector that requires grad, and it moves through some operations to give me the loss, once I apply that backward to the loss, it computes the gradient. So propagates everything backward and then populate the gradient. Okay. It's not the gradient, it's the gradient of the loss with respect to the theta. So theta.grad would contain the gradient. And we talked about this, if this wasn't clear, sort of, you should go through this other notebook. This is the basic gradient set without function, and you can, at each step you can verify. In the loop, it's going to be difficult, but this is the idea that we did. So, like the basic idea. So basic idea is here. So if you have a function and you call the backward, you get the gradient. Remember, this is the, you have to run it. To remind you. So here, for example, I have a theta, which is what? 1 and 2, right? Both theta 2 requires grad 2. And there's another theta 2 which doesn't require grad. The required grad is false. And I create a loss based on, this is a loss based on these two thetas. When I call the backward on this function, it's going to take the gradient with respect to all the vectors that went into constructing it and requires, they require gradients. And so that would be theta 100. So it takes the gradient would be 2 theta 0, 2 theta 1, and it evaluates it at 1 and 2, which would be 2, 4. So 2 and 4. Okay, so that procedure is going on. Yeah, is there a question? No. Okay, that procedure is going on here inside this. Okay, so when I do this, the grad property of beta is updated, which is also the same as theta, because they all point to the same thing. In any case, I don't need to worry about, but it's the beta grad is contain the gradient. And so here we're gonna move in the direction of the gradient. So this computes the gradient. They call it backward paths, forward, backward, algorithm, basically. That's where the forward and backward names come in here. So the backward is basically taking the gradient. And then you take the step. So beta minus equal is like beta minus. So beta is equal to beta minus this. Okay. Learning rate is the step size. which we pass, and then times the gradient. So that's the basic gradient descent. And then we zero out the gradient. This is also important because of the fact that the gradients are not zeroed out. So next time I call the backward, if I haven't zeroed out the gradient, it just adds into the square. It's an equivalent. So this we do because we don't want that to happen. And at the end, I clone the data again, append it to the list so that they have it record. So this is basic gradient descent in PyTorch. Okay. Sounds good. So what is the momentum version? The momentum version is very similar. So I just have another extra momentum parameter. And so this there's this extra z. So you do towards zeros like theta, this is another nice function. So it creates a vector of zeros the same shape as beta, right? And so this extra z, what we can do, it's gonna take, like it's gonna store our previous gradient. So you're gonna introduce a little bit of memory. And we have, let's see what it says. So I'm gonna compute the loss, and this is the same, do the gradient, and this is the key. So when I'm gonna calculate, I'm gonna do z times z plus 1 is gonna be equal to this momentum parameter is called alpha times dt plus the gradient. So this is going to be the gradient of function for the loss if you want this. And so current gradient just added to this alpha times dt, and then I take it a step in this direction. So I'm going to do let's say I do beta plus 1 is beta t minus this Lamian rate, which let's not remember, times the. So that's the simple thing. So instead of taking the step in the direction of the gradient, I'm taking the step in the direction of this, which is almost the gradient, but also like alpha times the previous value of itself. Okay, so when we initialize it with 0, right? So the first at t equals 0, there's nothing here, so it would be the gradient. Okay, and the next step, so this would store the gradient at time 1, and the next step, step 2, this would be gradient step 1, and this would be gradient step 2. So I'm gonna move a little bit in the direction of the previous gradient. So I form a linear combination of the current gradient and a bit of previous gradient. Okay, so this alpha is going to be depends on how big you make it. If it's 0, it's just the usual gradient descent. It's not there every time I just move in the direction of the gradient. If it's very large, I'm mostly moving the previous direction, but a little bit in the direction of the current gradient. The reason is previous gradient is probably slightly bigger. So this pushes us faster. That's the momentum idea. So you keep going, even if you don't have to go. But the current gradient tells you you don't have to go as fast, but the previous gradient tells you to move faster. So this pushes you faster. Forward. So this very simple idea has that dramatic consequence when you see, okay, so that's the gradient descent of momentum. And there are all the other bells and whistles that people try to like improve gradient descent, but this simple idea is very easy to implement. And you can see here that if it's the momentum, if it's 0, it's gradient descent. If it's like equal 1, you just never move. Sorry, you move very fast. You just move along the direction of the gradient or the initial gradient to infinity. So it's like 0.9 that I put. It's like almost always move, but because it's not exactly 1, you start towards the minimum because of this other term. Sounds good? You can understand what gradient descent and momentum is. Okay. So let's see the effect again. Gradient descent does that. So you can see it's like moving pretty nicely. Gradient descent with momentum, like momentum, let's say, for example, if it's 0.1, still like close to gradient descent, it's 0.5. still pretty, it pushes you a little bit, but not too much. 0.99, it goes off, right? Okay, so you don't really want to. So there's a limit. This is interesting, right? So we went back, but so you can see like the interesting, like pretty complicated behavior that these algorithms perform, even if the loss is convex. So there is some combination of these. So suppose, for example, I can change the learning rate. Let's see if I do 99. Is it going to convert? 9 is going to converge definitely. Still not converging. Yeah, so it's not going to help if I. Yeah, so 90. So there is a certain range of parameters for which this converge. And that range of parameter in complicated model is very tricky. 96 still converges. 98 doesn't converge. 97 still pretty close. So it's very interesting. We can't go over this, but there's a recent paper, for example, that studies like the. So let's say if I plot, for example, momentum and learning rate, so we have like the axis momentum and axis learning rate, and point is going to be like, let's say red if the model was learnable or trainable, maybe blue if it's not, so we diverge. So if you converge one color, we diverge another color. And they could use this for a complicated neural network, and it would look like a fractal. So as like we have like very complicated boundaries, and if you zoom in, it's still within that complicated boundaries, and within that complicated boundaries. So it was very hard to, in general, figure out what pairs of values would work. In this case, it's all we can figure out because the loss is like simple. Maybe in your homework problem, you'll see, for example, just without the momentum. This is the learning rate, there is a limit. So if I have the learning rate, so let's just move this back to the way where it was reasonable. And so the learning rate is also true. So if you do like 10, this is going to be good. Yeah, so this is going to also diverge. So there is a range, which in simple cases it's easy. In general cases, the more complicated models, more complicated loss functions. What do people do in practice? They often do the grid search. Okay, so you have a validation set, and you can first the convergence is easy to detect even without validation set, but you change the learning rates and other parameters that they have in learning with momentum. You do a grid search. You can create form a grid of values of momentum, learning rate, momentum. 0.05, 0.1, and then it's like 0.1, 2, 9, and then see, like check all the values. See when you convert it and also evaluate the validation loss. So validate the risk and pick the best. Sounds good. So optimizing more complicated functions becomes a little tricky, but we'll stick with this gradient with momentum. There are more advanced optimizers that we'll talk about. I'm just gonna, once you understand this, the more advanced ones do the same thing, but they add more bells and whistles. So you take a step and maybe like relay some of the coordinates differently. There are different ideas that people have developed over the years, and they settled into this particular set of ideas that work very well for, let's say, neural network. And they seem to do a good, stable job of reasonable gradients. But okay. So now, if you understand this, then basically like a few steps, then you can just train huge neural networks. The only difference is you just redefine the model, redefine the loss, and you're going to be good. So let me do an example here. So this is the real example. This is that breast cancer data that we have been looking at. We have been looking at in your homework problems. Let's do logistic regression on this. So this is real data. And I plotted it, and you can see there is like, it seems to be a natural linear boundary. And there's definitely noise, but let's see if this works. So we don't need these. So we load the data. So we talked about the way that this works. So we have like this, so there's a function that we can check. Because outputs the training and test splits. So I have X train, Y train, X test, Y test. Okay, so this is the tricky part. So I'm gonna concatenate. So what this does is I create a vector of ones. So shape is the, so you can see the size basically. Size of X train, so shape 0, 0 indexes the first one. So that's n basically the samples, samples and one. So that's the column of all ones. And I concatenate that column to X train along dimension 1, which is the second dimension, which is the columns. So it just adds the columns of all ones. Okay, so why do we do this? Anyone?
Intercept.
The intercept, yeah. So I've been ignoring the intercept for simplicity. So when I write this here, so there is no intercept, but as we know, as statisticians, this is sufficiently general. So I just have to augment my xi with a column of like with a vector of 1. So in the kind of notation that we have that xi is row vector, so I added 1 here. Okay, and so what happens is when I collect these, I get ones here. Okay, and then I multiply this by here is the theta star, please theta star, and this is going to be my b or intercept. And in machine learning, this is called W. So W is the weight associated with the real features, B is the intercept, which is associated with this one feature. So you can take up the whole thing and take it. Okay, so it's going to be B plus 1. So this is very common in regression, hopefully you know. And in practice, you really do want to have this oftentimes extra bias. Because otherwise, if you don't, what would happen if you don't put this here? What do you
Through pass through the
Yeah, so the decision boundary would be passing through the origin, and you can clearly see the decision boundary here is going to be passing through some other point. Okay? So if you don't do it, it's going to be some crazy thing, or maybe it's not even. It's worth trying to do that, but this is really important. Okay, so when I do this, now the decision boundary is theta star transpose x equal 0, which is W transpose x plus D equals 0. Okay, so this extra B allows us to have a shift. So this allows me to shape the vector. Okay, so now we have a three-dimensional, like n by 3 type float 32, which is good to have at least so that we don't get confusion. The rest is the same exactly. So the loss, same as before. Here you have to take a little bit of learning because this is different data. So tricky. So learning rate that, momentum that, 1000 step, start at the origin. There's a reason why. Different thing you can do random. And the forest graph has to be true because we want to keep track of the gradient. The gradient set is momentum, pass the loss, data, momentum, learning rate, number of steps. And at the end, I have this list. And this is like apparently this is what you can do. So you can stack them. This produces a portion so that it stacks all the tensors. And then detach because we don't want the gradient machinery to be there. I want to convert it to numpy array. So you have to detach the gradients of the machinery and then numpy so that it produces a numpy array. And then I plot. I don't know why I produce a numpy array, but that's what we did here. So that's the loss function. You can see that's just some crazy thing. Okay. But eventually it goes down. Okay. This good news. Like, so you have to do a lot of things.
So the first loss point is when we have the data at just 0. Right?
Yes.
Which is saying it's equal to the intercept.
Theta is not equal to intercept. It's just, yeah, so you're evaluating the model at the intercept. Right, and the intercept is, actually intercept is 0 as well. So intercept is the first one. So if you imagine, I added 1 here and then X train, so the intercept is the first. So I'm setting the intercept to 0, That's the first coordinate. And the two other coefficients of x as 0 as well. Okay, so what would happen is, if I plot this, you can see the trajectory. We started somewhere at 0. Where is 0? Yeah, 0 is here. So I believe. Yeah, 0 here and here. And about probably here. So initial point is somewhere here, probably here. I don't know. But then you can see that does a very crazy move. So this is moving here and then passes through like a region which is like oscillatory and then just shoot it up. The last point, and then this is the, you can see that that's the intercept. And it seems to be converging to something. And you can check it with like standard packages, which is scikit-learn package, which I'm doing down there to verify, but you can do it for yourself. But yeah, we started from, if you do the first, how do you plot the first, how do the first 10? How do the first 10? Yeah, okay, so 0, start from 0. You can see the move, and then we have to do a lot of moves to get to that point. What if I do the gradient descent, so you can see what happened here? What would happen if I do gradient descent? Is this going to work? Let's do gradient descent. I think it's my gradient descent.
Check
Sorry?
our
Gradient descent, right? Great. Okay, that's what it's doing. And it doesn't really converge that well. So is the learning rate too large? Smaller. This looks a little bit better, but it's still not converging that well. Okay, so what we get is, so the question is whether like the test performance is good or not, but you can see the loss is not going down as much as you hope. 10,000 maybe. Okay, now so you can see the effect of the momentum. So it just speeds up the convergence a lot. And so I end up like with much difficulty getting there. So yeah, so you can see like this simple idea of the momentum as we converge in tens, like 1,000 steps versus 10,000. Okay. It's one of those great ideas that cost effective. Show you again. It's 10,000, like 1,000 versus 10,000. And there is this more complicated software which I'll show you maybe. Well, add-ons. Maybe I'll show you here. Sure, maybe later. But okay, that's a lot less like wasted moves basically. Okay, and now let's see. Okay, I want to now do the prediction and maybe plot the level set. So this is our model basically. I'm going to give you like, this is the simple model that we define. We can do that for the class and then module that we did last time. We'll do that later. But I'm just we have a very basic model. It takes x, whatever data points that you want to value, the model that, and then calculates the sigmoid x times data. And so that's the probability. And so I apply the model to the training data. And then it says computing the decision. Compare the training and then take the mean. So that's the accuracy. And we get accuracy 8.9 on the training data. And if I do it on the test, I can do it on the test as well. Okay, there's something. What did we do wrong here? Let's- And Y train. So tell me what is wrong here. This problem. Oh, and do you know what's the problem? So the problem is, um, I haven't done the proper job of augmenting. So this is taking X with the augmented one. This is not, so let's not worry about that. So you have to augment this with a one. So this is not the proper way of so you have to add the count of one because it's expected to be three-dimensional. Right. So maybe I can do that quickly. Apply X this. Let's see if it understands to do that. Okay, it's smarter than me, so yeah. Okay. That's our 0.80. Good. So very close training and test errors. So apply decision boundaries. Okay, so that's the same function that we had. And then here I'm doing it a different way. So this is another way of we could have done this. So you think the first two elements, okay? That's the last two elements, the last two elements. Okay? 0, you can keep like 1 up to n. And then that plus the inconsist. You don't have to add the 1 to the other way. So I redefine it because this function takes three-dimensional. It expects a function of 2 variables. And then I pass the training to do this, and you can see this is the decision boundary found this point, and these are the level sets. Okay, so here things are more certain than 1. Here are like close to 0.5. Here's 0. So we did a pretty good job, and we got this classification accuracy of about 0.88, which is almost as good. You're going to do more complicated models later for this. So it's hard to beat this. So this is almost the level of like performance that is achievable. Sounds good. And then the rest you can check. I think this is just doing the scikit package, and it produces similar results to that. This guy like this, and these are the estimated data. So about 1 and 0.16. Let's see what we did. Yeah, so this is the same. So we managed to do this ourselves. We have to run the package and check that package is really similar. I think they're doing the Newton sort of like iterated the least squared. That's the classical way of doing logistic regression. You're not doing that. You're doing the very basic first order method. That's pretty well. Sounds good. Great. So next time I'm going to come back and extend this to multi-class classification and maybe a little bit more beyond. But very good about it.